Hello, everybody. I hope everyone can hear and see me. If so, I'm very glad to be part of this webinar. And first of all, I wish to say a good morning, good afternoon, good evening, good night to everyone that's attending this international virtual seminar on wood, pulp, and biomaterials from Federal University of Vicosa, obviously in Brazil. Before I start the speaker presentation, I would like to take from you just a few minutes to show some slides about the history of the Pulp and Paper Laboratory at UFV. So let's go on in the presentation. The Pulp and Paper Laboratory at UFV, we call by LCP. It has around 1,600 square meters of activity area on researching and teaching. So the history starts in 1970. Our history started together the growth of the cellulose pulp industry in Brazil. Initially, the LCP was attended by professors from Forest Engineer Department and someone from external to UFV. At that time, Professor José Lívio Gomide took over the coordination of the laboratory in 1972. However, in 1977, Professor Celso Felkel coordinated a startup of master sizing program on the pulp and paper technology with a very important partnership with Cenibra Industry and LCP UFV. So after 2 years after that, after 2 years, Professor Rubens Chaves de Oliveira and Professor George Luiz Coludetti started working at the LCP. And then this team developed an important work in teaching, research, and extension activity. So in 1998, the LCP was recognized by the Ministry of Science and Technology as the Brazil Center for Excellence in Pulp and Paper, and receiving funds from the support program for Center of Excellence in Pronex from the Brazilian government. So in that time, Professor Cláudio Mudado joined the LCP team in environment and cultural area, and he still work on very hard on this area. So, and at the year 2019, almost the present time, Professor Ana Márcia Carvalho joined the LCP team in the sector for the pulp and paper bleaching processing. So Professor Yara de Muner and Professor Marcelo Moreira as well. So at this time, at the year 2020, more precisely, the Pulp and Paper Laboratory enters in the social network and prepare its first international cycle of online lectures. Then, the LCP expertise has increased nationality and internationally and occupy a prominent position in the sector. So nowadays, LCP is considered the most important laboratory for professional training in research in Latin America in the pulp and paper sector. Actually, the following professors still work on in laboratory. Myself, as a collaborating professor on paper technology, and Professor Cláudio Mudado Silva on environmental control of the pulp and paper industry. Professor Ana Márcia Ladeira work on wood anatomy, chemical analysis, and pulping. And Professor Gleison dos Santos on forestry improvement for pulp productions. Yara Fontes de Muner work on in Pulp and Paper Technology, and Marcelo Moreira Costa on bleaching technology and in the pulp and paper industry. Also, Professor Sebastião Valverde is actually the Forest Department chairman and also coordinator of the graduate Lato Sensu program in Pulp and Paper Technology. At the whole team, I would say we have 20 collaborators, 81 graduate students, and 9 undergraduate students at this moment. And the main research lines that we are working on are eucalyptus clone selection for pulp and paper production, wood fiber morphology, wood chemistry, biorefinery, pulp technology, paper technology, and environment control area. So that's all I would like to say to you. Thank you very much for everyone. So this is my self-picture from 10 years ago. The time is go on. Thank you very much. From now on, let's start up the first speaker presentation. To do so, I would like to invite the first speaker, Juliana Jardim, to prepare for taking place to start the presentation. Juliana Jardim is actually a PhD student at North Carolina State University on Department of Forest Biomaterials. She received her master's degree in Pulp and Paper Technology at the year 2017, and the Bachelor degree in Forest Engineering at 2014 from Federal University of Vicosa, Brazil. Since that time, Juliana has worked on several projects associated with lignocellulosic processing. However, her PhD thesis is related to a better understanding of hardwood kraft lignins, as well as how their properties and structure change throughout the kraft pulping process. So I would like to say, please, Juliana, you can take place to start your presentation. Enjoy it.
Thank you for the introduction, Professor Rubens. Can you stop sharing your screen, then I can start sharing mine, please?
Can you see your screen?
We cannot share our screen at the same time. So you need to stop sharing your screen, then I'll be able to share mine. There you go. Yeah, thank you.
You're welcome.
All right. Well, thank you for the introduction, Professor Rubens. I would like to say good evening to everyone. It's a pleasure to be here today. I was part of the LCP crew for a while. I did my internship as an undergrad there, and I got my master's degree from LCP. I had a great time with the professors and all the students. So it's an honor to be here today as a speaker and to start to be the first speaker during this seminar. So I'm here today to talk about precipitation of kraft lignin. We will talk a little bit about the process, the parameters that are involved in the process, and we are going to talk about the material balance. Before we really start the presentation, I also want to thank my advisors here. My main advisor is Dr. Lucia, but I am co-advised by Dr. Jamil and Peter from West Rock. And these professors, they have been helping me a lot with my PhD. So here is the outline for my presentation today. Let's start talking about why should we care about lignin. We have heard so many times that you can make anything from lignin but money. Then we are going to go to the process, to the principles involved in the lignin precipitation, the parameters, the material balance, and then finally the final considerations. Here on the left side, you can see the lignin precipitated. Before I started my PhD, before I started working with lignin, I honestly knew that lignin was a wood compound that we wanted to remove as much as possible during the pulping process to produce paper. So I didn't even know how it really looked like. So here it is how it looks like. You can vary the color, but it's a brownish powder. And all right, so let's get started. Why should we care? We are more than aware of the implications of using petroleum-based materials. So we've been looking for process and like different process and pathways to produce materials in a more sustainable way. So we've been discussing a lot about biorefinery concept, which is the processing of biomass and using this biomass to produce fuel, power, and materials. With this being said, pulp and paper industry is a very good candidate for the biorefinery, since you can produce much more within the industry than just pulp and paper. For instance, 50 to 70 million tons of lignin are produced every year. So it's the lignin is very available around the pulp industry. And unfortunately, only 2 to 3% of this lignin is used for value-added use. Also, the extraction of lignin from the black liquor allows the increase of production, which is good. We are always the pulp industry is always looking forward to increase the production. And when you isolate the lignin from the process, you can add value to the industry. So you can increase the revenue of the company that's isolating this lignin from the black liquor. However, the understanding of this of lignin, it's very challenging. So lignin has been studied for over 100 years, and still there are so many doubts about its structure. It's a very complex aromatic structure. And since its understanding is hard, its isolation is hard, also the valorization, it's complicated. But a lot can be done. A lot can be done from it. And here are some examples, but I'm not gonna get into the application. Let's focus on the extraction process and what's involved, like what affects the extraction. Here, oops. So here, it's in these plots, you can see it's from a quick research on Web of Science. I used the keywords kraft lignin And you can see the increasing number of publications and citations over the past 20 years. And so even though there are many challenges using lignin, there are lots of challenges isolating lignin, the scientific community has found different pathways to deal with it and create value. I want to highlight here so if you use the keywords kraft lignin, you see this that it's increasing. But if you use the keywords hardwood kraft lignin, there is a huge gap of knowledge, and this was one of the motivations to starting my PhD project. Most of the research published now until now, most of them are regarding softwood lignins, and the hardwood is most of the time left behind. So if you're interested in knowing a little bit more about specifically hardwood kraft lignin, a few days ago, we published a review paper which gives you insights into the potential use of these hardwood kraft lignin to produce different materials. And then we talk about modification, fractionation. All right. So today I'm going to be focused on kraft lignin, but there are other lignin sources out there. And you can divide these lignins in sulfur-containing and sulfur-free. Among the sulfur-containing, you can find kraft lignin and lignosulfonates, which are the most common ones, which are the most available ones nowadays. But also you can find sulfur-free lignins, which are from the organosulf pulping process, soda, or from the second, like ethanol production of second generation. The characteristics and properties of these different lignins, they will vary in terms of molecular weight, in terms of water solubility, in terms of functional groups. So, for example, if you are looking for an application where sulfur cannot be in your product, you are going to go to a sulfur-free lignin. So every one of those lignins, they will have an application. But today we are going to focus on the kraft lignin, which has about 1 to 3% of sulfur and a low ash content, which varies between 0.5 and 3%. So now going towards the precipitation, like the process and the principles. In the beginning of this presentation, I mentioned that the extraction of lignin from the black liquor allows for increasing the pulp production. How does that happen? So here is just a picture showing the kraft mill. As you know, the black liquor, after the pulping process, goes to the chemical recovery. And the heart of this chemical recovery is the recovery boiler. And the recovery boiler is designed for to process a specific amount of solids. So if you want to increase your pulp production, you're going to have a surplus of solids going to the recovery boiler. So if you cannot process this surplus of solids in your recovery boiler, it's not viable. So then by creating another stream to the process, And then when you are able to extract this black liquor from the recovery boiler, you can then increase the production and send this surplus of black liquor to the recovery boiler. All right, so to get started talking about the process itself, I will use LignoBoost as our example. It's the most common one. And you use the black liquor from the evaporators. You don't use the black liquor that comes from the pulp, straight from the pulping process, not the weak black liquor. It's from the evaporator. So you use a liquor with solids content of about 40%. And then you acidify this black liquor with CO2. The acidification is from 14 to about 10. And then you go to a filtration step. Then the filter cake go to it's redispersed, and the filtrate goes back to the evaporation. So in this resuspension, sulfuric acid is added, and wash water is also added to decrease the pH from about 10 to 2.5. This suspension is then conditioned it has a conditioning step, and then from here it goes to a filtration, and then the filter cake obtained here is our final product, and the filtrate here also goes back to the evaporation. It's important to mention here that during the pulping and during the precipitation, there is a formation of hazardous volatile compounds. So you have to perform these precipitation in enclosed containers to recover these gases. So why is it important to do this conditioning that I mentioned after the acidification? This conditioning is important for the lignin molecules to agglomerate. So then they agglomerate little by little, and then they form larger clusters, which will help with the filtration and will also increase the final yield, the final recovery of lignin. So here it's a plot that shows you how important this conditioning is. So here at no time, the filtration, so it's showing with the filtration resistance. So at 0 time conditioning, the filtration resistance is much higher than after 60 minutes of conditioning. It's also important to highlight that different black liquors, even though they are from the same pulping conditions, they will behave differently due to its composition. Why is it performed the first filtration? It's important to do it to consume less acid, to reduce the pH from 9, 10 to 2.5. So the volume of suspension for you to adjust the pH is lower. And why should we perform the washing after the filtration? It's important to keep the sodium and sulfur balance because as I believe everyone that's watching today knows that the kraft mill is a closed cycle. So the chemicals used for the pulping process, they are recovered during the chemical recovery. So then this avoids makeup. Also, Another reason for washing the lignin is corrosion. So if you carry sodium with your final product, there are some applications. So then you can cause corrosion in the equipment when you're going to use when using the final product. And also you minimize wash water use. And why do we perform the resuspension? It avoids plugging during the filtration and also avoids uneven washing. And then also you avoid high sodium content. So here on the right side, you can see a table from my data from my work. This is from when I was isolating sweet gum lignin, and the results in red here are without resuspension, and then in blue with resuspension. So as you can see, the clays and lignin was increased after the resuspension. The acid-soluble lignin was decreased. The sugars contamination was decreased, and the ashes content, they were decreased from 9% to less than 1%. So it's extremely important to do the resuspension. Okay. Besides ligno-boost process, there is also ligno-force process. The idea of both processes is the same. The only difference in ligno-force is that there is an oxidation step before the acidification. And this oxidation with oxygen is performed to oxidize those gases that I mentioned before that are hazardous. So this oxidation makes them non-volatile. So here is just potential reactions and potential products of this oxidation. If you want to look deeper into the reactions, each compound, and when they're like the profile, how much they are, how much of them are released, and how much can be reduced after the oxidation, you can take a look at this paper published in 2016. So this table here is from this work. They kept track of every of those gases. And then here on top, unoxidized black liquor would be similar to the ligno-boost process. And then here, oxidized black liquor would be similar. It's representing the ligno-force process. And then I just want to compare the final total sulfur generated. So it's much smaller when you oxidize the black liquor before. All right, so there is a third process that's called sequential liquid lignin recovery and purification. Again, the idea is very similar. However, in this process, high temperature and high pressure are used. This process was invented in Clemson University in South Carolina. It's not commercial yet, but they claim that it's very effective and the filterability is really good. The yields are good, but they are not. This process is not commercial yet. And the difference here is that since it's applying high temperatures and pressure, we are talking about 150 degrees Celsius and even up to 800 kilopascal. The lignin is not like the suspension is not like a gummy suspension. It's more like more viscous, more liquid. So it's easier to handle. All right. In summary, among all these three processes, all of them, they use CO2 for acidification of the pH from 14 to about 9, 10. They will use sulfuric acid to reduce this pH from 9, 10 to about 2. And all of them will involve a combination of washing steps, conditioning steps, and filtration to remove the ash and contaminants. You can do the acid precipitation with any acid, with stronger acid, for example, hydrochloric acid. But there are implications. First, you have always to consider corrosion problems, which would be very with hydrochloric acid will happen. And also you don't want to hurt the balance, and you don't want to have to deal with this filtrate in a different way. So that's why CO2 and sulfuric acid are used, because they don't disturb this chemical balance in the kraft industry, in the kraft mill. And I just want to highlight here that you can use acid gradient to perform a fractionation of lignin. So here in this picture, you see that it goes from very dark to light color. We are from this paper varied the pH from 2.6 to about 0.7. So from each fraction here, the lignin properties, they will be different. There are other ways to techniques to isolate lignin from black liquor. We can name membrane ultrafiltration, for example. This method does not disturb the chemical balance of the kraft mill because it's based on size. So, and you can also do a fractionation, for example. You can do a sequence of different membranes cut off. So then you separate the lignin by different sizes. Another technique is through solvent and ionic liquid. So lignin is soluble in this some solvent in the ionic liquid, where when the other compounds, like the carbohydrates and the ashes, are not. However, it's a trade-off. The trade-off of these techniques that are they can be used, but they are usually more expensive. And for example, the solvents, you have to give some, you have to add to the process a recovery of these solvents. So that's why these other techniques are more for the fractionation of lignin instead of extraction from black liquor. All right, so in this slide, I want to bring up the functional groups present in the lignin. During the pulping process, the lignin structure undergo several modifications, and then it becomes soluble in the black liquor, right? And depending on the biomass, the proportion of these functional groups will vary, and also will vary in the lignin in the black liquor will vary. The most important functional group for the lignin precipitation is the phenolic group. So here you can see the equilibrium of dissociation of the phenolic group. And the precipitation is based on pKa. So pKa of a acidic group will tell you how strong it is. So, and here is just the dissociation constant. So the pKa of phenolic OH of phenolic groups is between 9.5 to 10.5. So when we do the acidification with CO2 of the black liquor, we are attacking the phenolic groups. So when the pH is lower than the pKa, the the ionized groups, they become protonized, and then the solubility decreases, and then the compound precipitates out. So that's how the lignin precipitation works. So, and when you decrease further the pH, for example, carboxylic acid, the pKa are between 3 to 4. So then these carboxylic acids will also precipitate out because they will be protonized. So the lower that you decrease the pH, you are giving the chance of different acidic compounds to be protonized and then precipitated. So now going towards process parameters. Here is a list of the main ones, but there is a lot of implications to the process. To begin with, the biomass. The biomass that you are using varies. So for example, from softwood to hardwood and grass, the composition of this biomass is different. So the lignin content is different. The lignin, the SG ratio of lignin will be different. The proportion of the functional groups and linkages will also be different. And then with all these variation between different biomasses, it will require different pulping process, different pulping conditions, and then will generate different black liquors that will behave differently during the extraction process. So then the biomass processing here, I'm going to focus on the kraft pulping, but it could be, for example, organosolv process or ethanol generation. But here we are going to focus today on kraft process. So then the age factor. So if we are using higher temperature, higher longer times, we are degrading more or less. We are going to have more or less lignin dissolved, and then like the condensation reaction. So it's going to be a higher molecular weight or lower molecular weight. So also besides H factor, the alkali is going to affect this black liquor. So the amount that you are adding, so the effective alkali and also the residual effective alkali will affect the sulfidity, the liquid to yod ratio, as well as kappa number. All right, so pH is the most relevant parameter. As a rule of thumb, the lower the pH, the higher is the lignin recovery. So this is because, as I mentioned before, because of the pK of the acidic groups present in the lignin. So when we decrease more, we are giving a chance to the weaker acidic groups to precipitate out. So this curve here is from acidification with sulfuric acid of softwood. So the profile might be different between which acid you are using, which process you are using, and which from which biomass you're obtaining, but the trend is going to be the same for every black liquor. And also, before I mentioned that you could use, for example, the gradient of pH as a fractionation technique. Here, if you take a look, this is the molecular weight distribution of 5 different lignins isolated from the black liquor at different pHs. So varying from pH 11.5 to 9.5, you can see the profile of molecular weight distribution is different between these lignins. So usually at higher pH, higher molecular weight, and lower pH, lower molecular weight. Now, talking about temperature, when all the other parameters are kept constant and you vary only the temperature, you are going to see a decrease in yield as you increase the temperature. The reason why is because you're making like the lignin more soluble. But if you take a look at the molecular weight distribution of these lignins precipitated at different temperatures, it won't affect much the molecular weight. And as I said, it's gonna be more soluble, the lignin, than it. So the higher the temperature, the lower is the filtration resistance. Here, another parameter of the process is ionic strength. So the salt content. On the left side, you see the results of no salt added, and on the right side, when salt is added, it's varying temperature too, but we can take a look at, for example, only at 45 degrees here. So when salt is added, you increase the lignin recovery. So the higher the ionic strength, the higher is the lignin recovery. And why is that? So when you are adding salt to your system, you are adding chards. So the screening of these chards will disrupt will help with the protonation of the ionized structures, and then it will precipitate out. Now talking about the black liquor composition, the lignin concentration will affect the extraction. So the higher the concentration, the higher is the yield. And the reason why is because when it's lower concentration, more water molecules are around the lignin molecules, and then this disturbs the agglomeration, and then this disturbs the agglomeration. Then during the filtration will cause the plugging and then less yield. The carbohydrates. So if carbohydrates are present in the system, it will be around the big agglomerates of lignin, and then it's gonna make the clusters more porous, and then this hinders the formation of the big clusters, and then during the filtration it's also a problem and will increase the filtration resistance and decrease your yield. So here, still talking about the carbohydrates, you can see the higher the carbohydrates concentration. So here, hemicellulose and separated xylose, the higher will be the filtration resistance. And then the solids content, as a rule of thumb, the higher the higher yields are obtained with higher dry content, because less volume of suspension will need to be acidified. But so if you are working with if you are working with a very viscous, which is going to be with high solids content, you have practical difficulties handling this black liquor. There are papers that use this recommendation of a range between 27 to 30% for softwood and 30 to 35% for hardwoods. Other two parameters are stirring rate and pressure. So pressure usually helps with the yield and also the time. So the process becomes faster when you apply pressure. And stirring rate, in the acidification from high pH to 10 and a half, it won't affect much. But after this 10 and a half, the higher the agitation, the faster is going to be the pH reduction. However, you cannot increase much this agitation, because you are going to disturb the formation of the big clusters, and then you are going to lose in yield, and you're going to affect the filtration. And also there is a foaming problem, that like it starts foaming, then it's an implication. The last one, I believe, that I'm going to talk about is the concentration of CO2. So if you take a look at this first graph here, the higher the concentration of the CO2, the faster is the pH reduction. But this CO2 has not to be, like, does not have to be very pure. So if you compare here 99.7% pure against 95%, the profile of acidification, the acidification rate is very similar. And also, no matter which concentration of CO2 you're using, the filtration resistance won't change much. So you are going to have to use more of the low concentration CO2, but it won't affect the filtration. Now, I just want to bring back the main parameters and bring them together. So here on the left side, these lignins were precipitated at 45 degrees Celsius, and then on the right side at 65, so a little bit higher the temperature, at different levels of ionic strength, varying between 0, 10, and 20%. So, and if we vary like 0.5 of pH, you see a much higher effect on the yield than when you compare only ionic strength or when you compare temperature. So again, I just want to emphasize how important the pH is over like all the other parameters involved in the extraction process. All right. Now, Let's move to the material balance. Now I'm going to talk a little bit more about the work that we've been doing here during my PhD. And I'm gonna present like the first chapter of my PhD dissertation. And if you are interested, here is the title of the. So we have recently published a paper regarding this. So if you are interested, you can take a look at. So for my PhD dissertation, the main goal is to understand how the lignin structure of different hardwoods, they change throughout the kraft pulping process. But specifically of this first chapter, we wanted to establish the material balance of the lignin precipitation from sweet gum, which is a hardwood, and pine, which is a softwood from kraft black liquors. So why did we do that? As I mentioned in the very beginning of the presentation, there is a lack of understanding of hardwood. Most of the publications, they deal with softwood. So we wanted to understand, to compare the behavior of these two feedstocks during the extraction, to then understand the difference between different hardwoods. So how did I do that? How did we do that? So we did the pulping to different extent. So we have 5 different levels of H factor for both raw materials. So in total, we evaluated 10 different black liquors. And the isolation process was performed in the lab. So I did some adjustments to a lab scale. I did use the LignoBoost principles. So I used 20% solids content, not 40 as it's used in the industry. I did the precipitation with CO2 until to reach a pH 9.5. Instead of the filtration, which is typical after the this acidification, I did centrifugation because, as I said, the filtration is it's hard because it gets very viscous. And then I read this, and then like my washing step, the resuspension, was with hydrochloric acid instead of sulfuric acid. And the reason why I use hydrochloric acid is because it removes more ashes than the sulfuric acid. And here I was not concerned about recirculating this filtrate, so it was okay. And then after this washing, I did centrifugation again. And I did another washing with acetic acid, but this is just for research purposes. We did freeze drying for these lignin samples. And then the hydrochloric acid could hurt the pump of the freeze dryer, but then I used the acetic acid to just wash the hydrochloric acid. And then I obtained this this lignin fraction at pH 9.5. But what I did different here of the LignoBoost process, from the first centrifugation, which would be the first filtration, I took this supernatant and I further acidified this supernatant to pH 2.5, and I followed all the washing steps to obtain a second lignin fraction of pH 2.5. So out of each black liquor produced a different H factor, I isolated two lignins at different pHs. So for the material balance, we did a characterization of the wood chips. We did a characterization of the pulp produced. We also did the characterization of the black liquor and as well as the solids precipitated after the protocol that I showed you. So the main parameters that we checked was pulp yield, residual effective alkali, the solids content of the black liquor, and clays and lignin, acid soluble lignin, and sugars of all these three solids. So how can you do how can you perform the material balance? So you know the lignin content in the wood. You know the pulp yield, and then you do the characterization of the pulp and then you know the lignin content of this pulp. Then you can calculate the lignin left in the pulp by making a relation between the lignin, how much you measure, times the pulp yield. And so then by difference of the lignin in the wood minus the lignin left in the pulp is what you have in your black liquor. So then it's easy to calculate the yield of recovery because it's just a relation between the lignin that was in the black liquor, then the lignin in precipitated divided by the lignin in the black liquor. Oh, and you can also do the calculation for the carbohydrates as well. So then you keep track of what was in the raw material, what went to the black liquor, and what's remaining in the pulp. Here there is an equation to calculate to predict the yield. This was published in 2010, and in another study, Zhu and collaborators, they used this model to estimate to predict their yield. And as you can see, the error, they don't really fall into the prediction. And the reason why is that this model was created for softwood. And in this second work, the researchers, they were working with a black liquor of a mixture of softwood and hardwood. So given the difference between the biomasses, the behave during the precipitation is different. So now showing a little bit of the results of this work, of our work. Here on the left side is the residual content of lignin and carbohydrates in sweet gum. So time zero here is the composition of the wood chips. And then as the pulping proceeds, how you can see the decay of cellulose, xylene and other sugars, and the decay of lignin. And on the right side, you have the same thing for the pine. So as I said, we had to keep track of every wood compound during the pulping process to know how much went to the black liquor and how much was remaining in the pulp. So then here we could calculate how much lignin was dissolved in the black liquor, which is represented by these green dots. So by the difference between the lignin that was in the black liquor and the one that was in the remaining in the pulp. And then the columns here, they represent the yield of precipitation. The blue part shows us the pH, the fraction precipitated at pH 9.5, and the red one at pH 2.5. So, as I said before, the behavior between hardwood and softwoods are different. So, for example, the gap between, if you take a look at cook time, 150 minutes for pine, almost all the lignin that was dissolved in the black liquor was precipitated. And then if you look at 150 minutes for sweet gum, there is a big gap between the lignin dissolved and how much was precipitated out. So here are the main conclusions of this first chapter of my dissertation. The pine lignins, they were much more easily precipitated from the black liquor, and they achieved better purities. And here's pine, but it should be sweet gum. And all lignins precipitated at pH 2.5, they were purer than at 9.5. But they increased a lot the pH, so the final yield. So you can see the size of these bars is big. But overall, the softwood, the pine, the performance was superior to the sweet gum. Now going to final considerations. Different applications for the lignin will determine the specifications needed for it. So some applications you can extract the lignin and use it as it is. But for example, as an additive in pellets. But some other for other applications, you will need some fractionation and sometimes modification. For example, if you need a water-soluble lignin, like kraft lignin, it's not water-soluble, but if you need the solubility in water, you are going to have to do some modification. So depending on what you want to do with your lignin, you can use it as it is, or you're going to have to do some purification or some treatment to use it. So the lignin, yes, shows a great potential to be used as fuels, chemicals, functional materials, and also to reduce the environmental impact. However, the efforts that show that this is commercially profitable are very few. And the main reason among all the papers that I've read, they claim like low yields and low quality of the final product. So here on this pyramid, I think the main takeaway here is that if you're doing the lignin extraction, you want to go to a value increase, for example, in final chemicals, because the value that the value from these chemicals is larger than just energy. For example, the price of it's higher, so then your return it's going to be better, even though the processing, even though it's going to need some fractionation or some purification, some modification, it's worth it. So the studies now, they are going more towards how to make it better to produce a more fine product. All right, with this said, I hope you guys didn't fall asleep. I would like to thank you for listening to the presentation, and I'm open for questions.
Okay, Juliana, take your brief. We got 2 questions for you. Mm-hmm. Both questions are very interesting. One question came from Rafael Machado Góes. The question is, when acid is added in the black liquor, can the residual of toluene be present in the lignin precipitation?
Professor, can you repeat the question, please?
Yes. When acid is added in the black liquor, can the residual of toluene be present in the lignin precipitation?
Well, I'm not familiar with the process for recovering toluene. I'm not quite sure if I remember the chemical structure. So I'm not sure if in this acidic condition, if it's soluble or not. So I'd rather not answer this question. I'm sorry. It was not my focus during this first part.
Okay. And the second question came from Marcelo Mugat.
Mm-hmm.
Could you comment a bit on the temperature requirement for precipitating softwood versus hardwood lignin?
Okay, Marcelo, thank you for your question. Specifically in our case, we did at room temperature. We didn't do process optimization. So I don't have a straightforward answer for you. So I've never worked in a lignin plant, but the temperature will affect the black liquor in terms of viscosity and solubility. And hardwood and lignin, hardwood and softwood lignin, their structure is very different. So in molecular weight, the hardwoods, they have smaller molecular weight, and softwood higher molecular weight. So usually hardwood is more susceptible to the changes than softwood, but I cannot tell you which temperature is the best, or I don't know. Then this is like, I believe you might have a better answer than me because you work with that.
All right. I got one more for you. This question came from Elaine Christina Lengosvicki. The question is, Juliana, is it correct to say the lower the pH, more pure is the lignin?
It's not a straight, no, it's not. In the case of specifically of our research, is that so in the carbohydrates that were present in the black liquor, they were isolated together with the fraction at 9.5. So that's why at pH 2.5, we had less contamination. But we are working with the same black liquor sample. So at 9.5, there was more contamination because it was precipitated first. So then this contamination didn't go to the fraction at pH 2.5.
All right.
Did I answer your question?
Okay, one more question. We got two more. This question came from Marcelo Muget. The question is, could you comment a bit on the strategies of mitigating extractives during the lignin precipitation, specifically on filtration resistance?
Again, Marcelo, I'm doing everything in lab scale. I didn't do optimization of the conditions. My focus is on lignin and how the lignin is structured changes I'm not taking a look at the extractives, so I cannot comment on that.
One more question. This question came from Frederick Poyet. Also, he says, thank you for the work. The question is related to slide 13. 13. The question is, you give composition in percentage. Would you have some values too, for example, in kilogram per income liters, to show the full interest of this resuspension?
Mm-hmm. So we can make a quick conversion to 100 grams. So let's say that we started with 100 grams of wood chips. So this 52.2 would be percent would be translated to 52.2 grams. So and then so it's very, it really changes a lot. So we are talking about almost 20%. And so if you also want to, I don't have it published, but I would be more than happy to share the results of this research with you. I have my email here. You can email me. I'll be more than happy to share this with you. There's a lot more calculation involved on that.
All right. One more question, Juliana. This question came from Kyle Michelino. The question is, can we extract lignin from the primary sludge, generating a kraft pulp mill effluent treatment plants?
Well, I've never took a look at this, but I believe yes. However, the yield must be very low, then I believe it's not worth it.
All right. One more question. This question came from Isabel Caligiorn. The question is, Juliana, thank you for the presentation. Can you please explain again the advantage of using chlorhydric acid instead of sulfuric acid on the process?
Okay, thank you for your question. For the industry, using hydrochloric acid is not interesting because of corrosion and you're hurting the chemical balance. So you're adding chlorine to the system. However, for lab purposes, for research purposes, you can use this because you're not going to recirculate the filtrate, and the salts that are formed during the washing are more water soluble than the salts that are formed with sulfuric acid. So it's more efficient removing the ashes.
All right. One more question, Juliana. This question came from Daniel Lima. The question is, hello, how I can reduce the percentage of the lignin in the fiber? Actually, precipitation?
Can you repeat the question, please?
Yes. How can I reduce the percentage of the lignin in the fiber? I understand precipitate over the fiber, over the surface of the fiber.
So how can you reduce reprecipitation of lignin, right?
Yeah.
So this is going to be based on pH. So at higher pH, lignin is soluble, so it won't reprecipitate. So if you don't want lignin reprecipitation, you want to keep your pH high. So in the pulping process, you want to keep your residual effective alkali high. But if you go to pH lower to 11, 10 and a half, the lignin starts to precipitate out. So it's all based on pKa and this ionization and protonation. So if you don't want lignin, you keep pH high. If you want lignin, you bring pH down.
All right. One more. This question came from Marcelo Manget. The question is, first, he made a comment. Theoretically, dissolved xylem might impair more the filtration in hardwood when compared to softwood. Now the question, did you have experience of that in your lab experiment? Do you have result on this?
Yeah, definitely. The xylem content. Huh?
He said, congratulations, I guess.
Thank you. Yes, definitely. The xylem is a much bigger problem when we are talking about hardwood than softwood, given the xylem is the main hemicellulose in the hardwood, and also it's somewhat resistant to the pulping process. So I had the lignin precipitated from sweet gum, which is my hardwood, was much more contaminated with carbohydrates than pine. So here I just have the residual in the pulp, but in the paper, I have the content that went to the black liquor, and this gap here we attribute to the contamination with carbohydrates. So it makes we cannot affirm that it's LCC, that the carbohydrates are linked to the lignin, but they are associated somehow, and it makes the lignin of sweet gum much more soluble than the pine.
Okay, I hope everybody can see me. And I would say thank you to Juliana for excellent presentations.
Thank you.
And I would say thank you for all the attendants. Probably enjoy your presentation. It's very nice experiment and results. So now we're gonna close it, this section, and then let's go for the next days for more very good presentation like this.
I look forward to it. Thank you very much again.
Thank you everybody to attend this international seminar. It's very interesting topics come on the next days. See you later. I will close my section.